Hello everyone. In this session we are going to learn how to solve a system of linear equations by using Cramer's rule, and Cramer's rule is based on determinant. So what is a determinant? Determinant can be found from a matrix, especially a square matrix. So here our focus is on solving linear equations by Cramer's rule. So you know already how to solve a system of linear equations by Gaussian elimination method, or which is known as row operation technique or row echelon technique or back substitution technique. But here we will solve the same system by using Cramer's rule. So first of all, I need to remind you that is a system of linear equations can be consistent, can be inconsistent. So consistent means has solution, inconsistent means no solution. A consistent system, since it has solution, so can be classified into two parts, that is, the system may have one or unique solution. The system may have many solutions. So you already know how to solve a system of linear equations that can be consistent, can be inconsistent, that has one solution, maybe with many solution or no solution. So we know how to solve this type of systems by using Gaussian elimination technique. But here we will solve same type of system of linear equations by using Cramer's rule. So first of all, I need to mention that Cramer's rule has a limitation. It is only applicable for the system that has one solution. It is not applicable for this part and this part. That means it is only applicable for one or unique solution. So first of all, besides this idea, we need to also know what is a matrix. So matrix is just an arrangement where there are rows and columns. So you know that if the number of rows and the number of columns are same, then that is known as a square matrix. So suppose we have 2, 3, 4, 5, 6, 7. So this is a matrix. It has 2 rows and 3 columns. So we write this is by 2 by 3. We are pronouncing this one as 2 by 3. Although we are writing 2 multiplication 3, we will pronounce this one as 2 by 3. That means this is the order of the matrix. Okay, that has 2 rows, 3 columns. Order means what is the size of the matrix, or what is the dimension of the matrix. It means it has 2 rows and 3 columns, but mathematically we write by 2 by 3, row by column. So the first thing is that this is a matrix where the number of rows and the number of columns are not same. So this type of matrix is known as rectangular matrix. But suppose we have a matrix that is 2, 1, 5, minus 4. So this matrix has 2 rows and 2 columns. So here the number of row and number of column are same. That means this is a square matrix. So you need to remember that only if we have a square matrix, then determinant is possible. We can find a specific value for this matrix. that value is known as determinant. And if you can find the determinant, it is easy to apply Cramer's rule, because Cramer's rule is totally based on determinant. So first of all, whenever you are solving a system of linear equations, you will generate a matrix that is a coefficient matrix. You know what is a coefficient matrix already? Okay, so if you have the matrix and it is a square matrix, then only you can find its determinant. Then you can go for Cramer's rule. So here we are going to discuss all these things. So based on determinant, a matrix can be classified into two parts: non-singular matrix and singular matrix. So what is a non-singular matrix? A square matrix A is called non-singular if its determinant is not equal to 0. That means the determinant has a value. Then that square matrix will be called a non-singular matrix. And what is a singular matrix? If we have a square matrix A, then it will be called a singular matrix if the determinant is 0. So first of all, we have to understand that Cramer's rule is only applicable for non-singular matrix. That means the matrix that has a determinant that is not equal to 0. So Cramer's rule is only applicable for non-singular matrix. That means the determinant is not equal to 0. So suppose we have a system of linear equations. So from that system, we are at first finding a square matrix from the coefficients. If the square matrix has a determinant that is not equal to 0, then only Cramer's rule is applicable, otherwise not. So Cramer's rule is not applicable for singular matrix, remember. So since non-singular and singular matrix are based on determinant, or Cramer's rule is based on determinant, let's see how we can find determinant of any square matrix. So here is one example. Suppose we have a 2 by 2 matrix. Let's say A, B, C, D. So here I need to mention that matrix is denoted by this type of notation, or with this notation. You can use a square bracket or parenthesis, and inside this you have some entries: entry A, B, C, D. But if you are going to find the determinant of any matrix that is square, where number of rows and number of columns are same, so in that case the determinant can be written by this, with vertical bars. You can see here and here. So you just have the same matrix A, B, C, D with a square bracket, but the determinant is written by A, B, C, D with this vertical bars, or it is also known in this form: determinant of A. That is the matrix A, B, C, D. This is also we can write. So here we will use only one notation. Just for simplicity, we will use this vertical bar for determinant. So first of all, suppose you have a square matrix, this one, where the entries are A, B, C, D. So if you have to find its determinant, then it will be AD minus this CB. So this is about determinant of any square matrix that is of 2 by 2, where there are 2 rows and 2 columns. Similarly, suppose we have a matrix, this one, where there are 3 rows and 3 columns. So for this matrix, the determinant is denoted by this vertical bars, and we have the same entries: A, B, C, D, E, F, G, H, I. So the determinant of this 3 by 3 matrix can be found by this way. You can see, if we can write this by this way, then every time we have new 2 by 2 determinants, and you know how to find the determinant for 2 by 2 matrix. So here you have a 2 by 2 matrix, 2 by 2 matrix, 2 by 2 matrix. So now we will learn how to write this to this. So suppose we have a 3 by 3 matrix, just like this one. So how we will find its determinant? Determinant is just a value of a square matrix. It is just a number. So it can be found by this way. If we have a 2 by 2 matrix, then it is easy to find. But if we have a 3 by 3 matrix, then it can be found by this way. So first of all, you need to know what is a minor and what is a cofactor of the entry of any matrix. So suppose you have a matrix 2, 3, 4, 6. If we need to find the minor of this entry, let's say it is known as minor. Minor of any entry of a matrix can be found by cancelling the respective row, cancelling the respective column. Then what you have? Only you have 6. That is the minor for entry 2, minor of 2. That is how we write. So minor of 2 is 6. Besides minor, you have to also know what is the definition of cofactor. Cofactor of any entry. So first of all, you know that a matrix has entries A11, A12, A21, A22. That is, this is the entry whose position is in the first row, first column. This is the entry whose position is in the first row, second column. Similarly here, the entry is at the position second row, first column. Entry is at the position second row, second column. So if we have to find the minor of any entry, let's say 2, that is actually 6. But what is the cofactor? Cofactor is the same value 6, but before 6 we have a sign plus or minus that we have to determine. So that can be determined by row and column. So we will understand by this way. Suppose we have a matrix, let's say we have a matrix here A that has entries 3, 4, 5, 2, 1, 4, 3, 9, 7. Let's say we have a square matrix here. Now we want to find the minor of the first entry. Minor can be found for any entries. Remember, minor can be found for any entries. So let's say we want to find the minor of entry 4. So minor of entry 4 can be found by this way, by cancelling its respective column and its respective row. Whatever you have 2, 3, 4, 7. So minor is 2, 3, 4, 7. That means you have to find the determinant of this 2 by 2 matrix. That is cross multiplication of 2 and 7, 14, minus 3 and 4, 12. That is 2. So minor of 4 is actually a value 2. Now remember, the matrix A has A11, A12, A13, A21, A22, A23, A31, A32, A33 entries. So if we now have to find the cofactor of this 4, that is also 2, but before 2, is it plus or minus, that we have to determine. So that can be determined by a technique. Have a look on this 4. What is its position? It is at 1, 2. That is first row, second column. So always with minor, let's say minor is denoted by M. Then before M, you have to always write -1 power I plus j. What is I? I is the row, j is the column. So let's say for this 4, what is the cofactor? Cofactor will be -1 power something plus something times m. So -1 power, its position is at first row, second column. So 1 plus 2, I plus j. That means minor of this 4 will be -1 power 1 plus 2 times 2. So we are getting -1 power 3 times 2. So you know that -1 power 3, that is actually -1 times 2. So you are getting -2. So now you are sure that before 2 we have minus. So you can think about cofactor in this way. Cofactor of any entry is actually -1 power I plus j with the minor. So cofactor and minor are actually same. Minor is just a value of any entry, and cofactor is the same value but with plus or minus. So suppose now we have to find the minor and cofactor of, let's say, any random entry 5. So what is the minor of 5? That can be found by this way. We have to cancel its corresponding row and corresponding column. What you have? Only you have 2, 3, 1, 9. So you have to find its determinant. 2, 3, 1, 9. Let's find the determinant. That will be the minor of this 5. So we can write that minor of 5 is 2, 3, 1, 9, its determinant. So what is the determinant of any 2 by 2 matrix? You already know. That is 2, 9, 2 times 9 minus 3 times 1. That is 18 minus 3, 15. Now what is the cofactor? So cofactor is the same value, but before you have to write -1 power I plus j. Now you have to note down the position of 5. It is at first row, third column, 1, 3. So write by this way. First row, third column times 15. So -1 power 4, 15. You know that -1 power 4 is actually +1. So 1 times 15, that is 15. That means the cofactor is +15. So cofactor is just same as minor, but cofactor defines you positive or negative values. So finally you now have the idea of minor and cofactor. So we have seen here how to find minor of or cofactor of any entry of a matrix that is of 3 by 3. Let us think about the minor and cofactor of, let's say, a 2 by 2 matrix. Let's say we have 1, 3, 4, 7. So this is a 2 by 2 matrix. So if we have to find the minor of 4, let's say minor of 4, what we have to do? We have to cancel the respective row, respective column. What we have only? We have 3. Actually determinant of 3, just like this one. Determinant of this. And here we have only this number, so determinant of 3. So determinant of 3 is actually 3. So that's why no need to make it complicated. You can just write directly 3. So this is the minor. Now if we have to find the cofactor of 4, that is also 3. But before 3, is it plus or minus? That we have to determine. So that can be found by minus 1 power I plus j. I is denoting row and j is denoting the column position. So 3, where is it? It is at first row, second column. First row, second column. So we are getting minus 1 power 3 times 3, that is minus 1 power 3 times 3. So you know that minus 1 power 3, that is minus 1. So minus 3. So minor of 4 is 3, but cofactor of 4 is minus 3. So that is the relation between minor and cofactor. So let's get back to our main discussion. We are learning how to find determinant of any matrix. So here we have a 3 by 3 matrix and the determinant is this one where we are using vertical bars. Now we have to find the determinant of this 3 by 3 matrix. So how we can find this? This is by this way. So here you can see that before there is a plus, here we have minus, plus. So this plus, minus, plus have directly been found from the cofactor. I have written here directly. So for any 3 by 3 matrix, if you are going to find the determinant, use this pattern: plus, minus, plus. Okay, so you can directly write this because you already know how to find the cofactor. But if you want to describe, you can also explain, no problem. So have a look how to find the determinant. First of all, A times its minor, that is E ace Fi. You can see here, that is you are going to find the determinant. Then there is a minus coming. Now find about B. So for B, respective row, respective column are cancelled. You have dg Fi, dg Fi. You can see. Find its determinant. Then there is a plus. Now find the minor of C. So how to find the minor of C? Respective row, respective column are cancelled. You have to think about the determinant of dg Eace. Have a look, dg Eace. Now the determinant is very easy to find. So you can see that all the way now we have this type of 2 by 2 determinant. So let's find A. Now what is the determinant of this? It will be Ei minus ace F. So that is how we can find. part by part. Then there is minus b. Now find out the determinant of this. That will be di minus gf. Then lastly you can see you have plus c. Find now the determinant, this one, it will be dAs minus ge. So this is about finding the determinant of 2 by 2 matrix or 3 by 3 matrix. You will get to know the idea again if we have a look on two examples. Suppose we have the matrix 2 1 minus 5 6 and its determinant is this one. So how to find the determinant? It will be 2 times 6, that is 12, minus, this minus is coming from the formula. Have a look. So 2 times 6 12 minus 1 times minus 5, that is minus 5. So you can now simplify it. 12 plus 5, that is 17. So this is how you can find the determinant of this type of 2 by 2 matrix where there are 2 rows and 2 columns. Similarly, if we have a 3 by 3 matrix like this, there are 3 rows and 3 columns. So how to find the determinant? You have to find the minor of 5 minus 1 minus 2, just like here, minor of A, B, C, A, B, C. You don't need to think about the cofactor, because always if you have a 3 by 3 matrix, first part will be plus, then minus, then plus, plus minus plus. So this is how you have to think about. No need to think about the cofactor, only minor and this pattern plus minus plus is enough. So here, first of all, let's find the minor of 5. So you have to write 5 times its minor. Minor of 5 will be respective column and row are cancelled. You have 1 4 5 3, 1 4 5 3. Find its determinant. Then there is a minus. You can see there is a minus. Find the minor of minus 1. You have to write minus 1 times the minor. Respective row, respective column are cancelled. You have 3 2 5 3, 3 2 5 3. Find its determinant. And lastly, you have to find the determinant of minus 2. So minus 2 and its determinant is respective row, respective columns are cancelled. You have this 3 2 1 4, 3 2 1 4. So now you can easily calculate. Have a look. 5 times 1 times 3, 3. There is a minus. 4 times 5, 20. Here minus minus plus. Now determinant of this part will be 3 times 3, 9. 2 times 5, 10. Plus minus minus. Minus 2. Now find its determinant. 3 times 4, that is 12. There is a minus. 2 times 1, 2. So you are done. Now it is just simple calculation. So you can see that the determinant is minus 106, that is not equal to 0. If the determinant is not equal to 0, you know that that matrix is known as non-singular matrix. So you need to remember this definition. What is a non-singular matrix? So now we are ready to know what is a Cramer rule. So Cramer's rule is named after the mathematician, Genevan mathematician Gabriel Cramer. So suppose we have equations like 2x plus 3y equals 4 minus x plus 4y equals 7. So we have two equations, that's why this is a system. All the equations are linear because the variables are with power 1. So these are linear equations, system of linear equations. So if we have two equations and what will be our target then? Our target is to find the solution of these two equations. Solutions means x and y. We have to find what is the value of x and what is the value of y. So if we have these two equations with two variables x and y, then how to find the solution x, y? Solution can be found by this way. X equals d sub x divided by d, y equals d sub y divided by d. We will try to discuss what is d, dx and dy later on, but for now note down that if we have two equations with two variables x and y, then x and y can be found by this: x equals dx divided by d, y equals dy divided by d. So here first of all I need to note down here that all these d sub x and d sub y are actually determinant. You know how to find the determinant, so these are determinants. Similarly, suppose we have equations like this: 3x plus 4y minus 2z equals 8, x plus 2y plus 3z equals 7, and 2x minus 5y plus 4z equals 5. So this time we have three equations with three variables x, y, z. All these equations are linear equations because x, y, z has power 1, 1, 1, 1, 1, 1, 1, 1. So these are linear equations. So we have a system of linear equations. Now if we have to solve this system, that means we are going to find the value of x, y and z. So if we have three equations with three variables x, y, z, then x can be found by this way, y and z can be found by this way. So x equals d sub x divided by d, y equals d sub y divided by d, z equals d sub z divided by d. All these d, dx, dy and dz are nothing but determinants. So we are going to learn now Cramer's rule. So have a look again how to find the solution. Solution for two equations with two variables x and y can be found by this way. Solutions for three equations with three variables x, y, z can be found by this way. Now we are going to see one problem. Suppose we have three equations with three variables x, y, z. So you know, by Cramer's rule, x, y, z can be found by this way. So Cramer's rule is only applicable for non-singular matrix. That means the determinant should be non-zero. The determinant can't be zero. It should be non-zero. So determinant of which matrix? The coefficient matrix. Have a look on the left side. The coefficients a11, a12, 13, 21, 22, 23, 31, 32, 33. These are the coefficients of x, y, z. So if we try to write a matrix by only with these coefficients, then that matrix is known as a coefficient matrix, you know. So for a coefficient matrix we can also find its determinant. Have a look, here is the determinant. Determinant of the coefficient matrix is a1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So you have to check at first, before applying Cramer's rule, that whether the determinant of this coefficient matrix is 0 or non-zero. If it is non-zero, then only you can apply Cramer's rule, otherwise not. Okay, so that is the limitation of Cramer's rule. Cramer's rule is only applicable for one solution. It doesn't give us any conclusion for many solution or no solution. It is only applicable for one solution. That means if the determinant is not equal to 0, the determinant of the coefficient matrix is non-zero, then only Cramer's rule can be applied, otherwise not. So you can easily understand that for some problems, if you directly get d equals 0, then Cramer's rule is not enough to leave a final comment. Okay, so for d equals 0, the only hope is Gaussian elimination method that you already know. Here we are learning only Cramer's rule. Okay, so remember, the determinant of the coefficient matrix should be non-zero. So our target is to know what is d, d sub x, d sub y and d sub z. So have a look. You already understood what is d. D is the left side coefficient matrix and its determinant, this one. What is d sub x? So d sub x is a same type of determinant, but have a look, the only difference between d and dx is here. You know that the first column is for x, second column is for y and the third column is for z. So whenever you are finding d sub x, then in this first column, in the first column of x, you have to place the right side values b1, b2, b3. Whenever you are finding d sub y, then you know first column is for x, second column is for y, third column is for z. You are finding d sub y, then d and d sub y are same, but in the place of y in this column you have to input the right side values b1, b2, b3. Similarly, whenever you are finding d sub z, it is just same as d. Have a look, a1 1 2 1 3 1 1 1 2 1 3 1, a1 2 2 2 3 2 1 2 2 2 3 2, but x, y, z columns. So you are finding d sub z, that means in the last column, that is in z column, you have to input b1, b2, b3, and now all are determinant. You know how to find the determinant, just like this way. So here there is one problem given. You have 2x plus y minus z equals 3, minus x plus 2y plus 4z equals minus 3, x minus 2y minus 3z equals 4. So this is a system of linear equations. There are 3 equations, that's why this is a system. If you have more than one equation, that will be called a system. These are linear because all the variables are with power 1. So this is a system of linear equation. Now we have to solve this by Cramer's rule. First of all, we have to check whether Cramer's rule is applicable or not. So you know that you have to find the solution of these equations, that is you have to find x value, y value, z value. Together x comma y comma z will form a unique solution. So have a look. For x, formula is d sub x divided by d. For y, d sub y divided by d. For z, d sub z divided by d. So let's find at first d. So d is the left side coefficient matrix, that is 2 minus 1 1 1 2 minus 2 minus 1 4 minus 3 minus 1 4 minus 3. So just the left side entries are in this determinant. Now you know how to find the determinant of this 3 by 3 matrix. So after calculation we are getting 5. That is not equal to 0. That means this is a non-zero value. So it ensures that Cramer's rule is applicable. That means this matrix, this left side coefficient matrix, is a non-singular matrix. So we can apply Cramer's rule. That means these formulas can be applied. So as we have found that the determinant of the left side coefficient matrix is 5. Now let's find d sub x, d sub y, d sub z. So what is d sub x? D sub x is just same as d, but in the first column, that is in x column, you have to input this right side values, that is 3 minus 3 4. So 3 minus 3 4, and now find the determinant, it is 15. Similarly, d sub y, in d sub y, just think about the first column is x, second column is y, third column is z. You are finding d sub y, that means in the y column input the right side values, 3 minus 3 4. So 3 minus 3 4 is plugged here, and finally you can easily find the determinant, that is minus 10. And similarly d sub z, it is just same as d, but in the third column you have to input the right side values, 3 minus 3 4, and now you know there is another new matrix, or suppose a new determinant, you can easily find its determinant, that is 5. So now you have all values d, d sub x, d sub y, d sub z. So now find first x. X has the formula d sub x divided by d. So d sub x is 15, d is 5. 15 divided by 5, that is 3. So x equals 3. Similarly y, that is d sub y divided by d, minus 10 divided by 5, minus 10 divided by 5, that is minus 2. So y is minus 2. And similarly z, d sub z divided by d, d sub z is 5, d is 5. So 5 divided by 5 is 1. So x, y, z is 3 minus 2 and 1. We are getting a unique solution. So this is how we can apply Cramer's rule. So this problem is for a system where 3 equations are given with 3 variables x, y, z. So same rule is for 2 equations with 2 variables x and y. So if we have this type of system, you can easily find the solution x and y. So here the left side coefficient matrix will be a1 1 1 2 2 1 2 2. So the determinant of this matrix should be non-zero, then only Cramer's rule will be applied. Now x equals d sub x divided by d. So whenever you are finding d sub x, remember the first column is for x, second column is for y. So in the first column you have to input the right side values. Similarly, whenever you are finding d sub y, then first column is for x, second column is for y. So in the second column input the right side values, b1, b2. So you can easily find all the determinants and you will get the solution for this system. So similarly, here there is a problem. We have a system of equations. We have 2 equations with 2 variables x, y. So whenever we are solving these equations, it means you have to find x and y. So x has this formula, y has this formula. At first you have to find d, and you have to ensure whether Cramer's rule is applicable or not. So we can see that Cramer's rule can be applicable. Here is the left side matrix 2 1 1 minus 1 2 1 1 minus 1. Now find its determinant. It is minus 3. Minus 3 is not equal to 0. That means Cramer's rule is applicable. So now find d sub x and also d sub y, because if you have to find x and y, you need d sub x, d sub y. Already d is in your hand. Now d sub x, the first column is for x, second column is for y. Just in the first column input 5 and 1. Whenever you are finding d sub y, just in the second column, that is in the y column, input the right side values 5 and 1. So you can easily have the results. So this is how Cramer's rule can be applied. Now you can practice from problem set 10. So here there are some problems given. You can apply Cramer's rule and try to solve. In this problem set, the first problems that has been given that are based on Gaussian elimination method, and below you will see there are some problems that are based on Cramer's rule. So I hope you have understood Cramer's rule, and now you have to practice, and then you will totally get the idea. So that's all for today. Thank you.